We're going to look at a type of differential equation known as the Cauchy Euler equation. And it's an equation that looks like this, where these coefficients here are constants. Okay, so the a's are constants. And notice we have these extra powers. Now, what makes this a Cauchy Euler equation is the fact that, notice we have an nth order derivative right here, the nth derivative, and here a degree n. So notice that the coefficient here of this nth derivative is x to the nth power. Likewise, the nth n minus first derivative here is paired with this x to the n minus 1. So when we have that situation, this type of equation, this is the Cauchy Euler, and we want to explore a method for solving that particular type of equation. So let's suppose we have this one, a second order differential equation, and this is a Cauchy Euler. What we do is we assume that the solution, one of the solutions, is x to the m. Okay, like before, we assumed a solution to an equation. We looked at a homogeneous differential equation with constant coefficients. We said, well, the solution, let's assume it's e to the m, but now it's x to the m. And just like before, we go through and differentiate it. So if I've got y equals x to the m, I differentiate it. There's the first derivative, there's the second derivative. And then we go back and we plug those into the function. So I plug in the y double prime in for the y double prime. And we get it right here. I plug in the y prime for the y prime right there. And then, of course, this y on the end, that's just x to the m. Okay? So we got all of that plugged in. Now, notice that this x to the second power multiplied with this x to the m minus 2 just gives us x to the m. And the same thing happens over here. The x to the first power multiplied by the x to the m minus 1 gives us x to the m. And when that happens, notice we've got these x to the m's running around here. So I'm going to factor that out. There's the x to the m right there. I just factored it from these three spots. And then here's what we have on the inside. Now, if I do a little bit of algebra here, you'll notice that I've got am squared minus am plus the bm plus c right there. If I group my m's together, I've got am squared times b minus am plus c. Yeah. Now, at this point, I can go ahead and solve this because this is just a quadratic equation. And I can use the quadratic formula where I have negative b plus or minus the square root of b squared. Well, you know, the coefficient of the first power term. Okay. So this negative this plus or minus the square root of this squared minus 4ac all over 2a. Okay. And of course we get two answers, and here is our solution for that particular homogeneous equation. So that's the overview. Now, let's look at an example here. Let's suppose we've got this one. Okay. This is a Cauchy Euler equation. We assume the solution is x to the m. That's one of the solutions. We go through here and differentiate, and we plug back in. Okay. And we go through all of the algebra. We end up with this. Okay. And then working that out, we get this, putting the m's together. See? We get this. So what it amounts to is we end up with x to the m squared plus 7m plus 10. So this is like those auxiliary equations that we've dealt with in the past. We know how to deal with these. We can factor, or if we couldn't factor, we could use the quadratic formula. But notice we get m equals -5 or m equals -2, and there you have your solution right here. Y equals c1 x to the -5 plus c2 x to the -2. There you go. And what we've just done is solve this homogeneous equation. Now we're going to stick with the homogeneous type for now, and then in a minute I'm going to say, okay, let's look at a non-homogeneous case. Okay, so there is the first one. Now notice we have two distinct roots here, -5 and -2. Now let's go down and look at this next one. Okay, this one right here. We go through the process, assuming that x equals, or y equals x to the m. Go through this process. And this time, we come up with this equation to solve. And this gives us this, okay? M plus 1 squared equals 0, which gives us m equals -1. Okay? So, we have one solution, not two distinct solutions, just one. And what I want to do then is I want to go back and find the second solution. Okay? So here's what we've got. And I want to go back and find that second solution. We use this method of reduction that we learned in previous sections, reduction of order. So what I'm going to do is I'm going to take this solution. So this is y1. Now remember how the formula goes. It goes like this. It says that if you want to find the second solution, take the first solution, integrate that with the denominator being the first solution squared, and up here, e to the negative p dx. Okay, so this is the formula that is going to give us the second solution. Okay, so let's look back and see what we have now. I go back to this equation, x squared y double prime plus 3x y prime plus y, and let me get this set up. I'm going to divide through by x squared. Okay, so here's my x squared. I'm going to divide through by x squared to get it to where I can find the p. Okay, so this is the form of the differential equation that I use. Notice I divided out the x squared. So now look what p is. P is 3 over x. Okay? So dig this. We've got x to the -1. That's our first solution. Over x to the -1 squared. And then up here we get, it's negative. So I'll put a negative there. And this is going to be -3 integral 1 over x dx, which gives us this, okay, which brings us to this, which brings us to this, and we solve it. So notice what we have here. We have x to the -1 log x, okay, and this, notice, here's our first solution. Here's our first solution times the log x. And that's the way these are going to work. If my first solution had been x to the -2, then what I would have is I would have c1 x to the -2 plus c2 x to the -2 log x. So for these second order differential equations. Okay. Now, and the second order is all we're looking at right now. Okay, now, so we've seen what happens when you have two distinct values for m, and then we see what happens when you have one value for m. Okay, so now let's look and see what happens when you have complex values for m. So let's look at this differential equation. We go through and we end up with this equation where we're solving for m. We put it into the quadratic formula and we get 2 plus or minus I. Okay, so there's 2 plus or minus I. And so here's our solution right here. Okay, which we can write this way, because we know how to work with exponents. So this is the same as this. Now, I want to make this solution look neat and cool. Okay? So what I'm going to do is I'm going to recognize that this part right here, I can rewrite this part as this. Okay? It's just a little trick. In mathematics, it's a lot of tricks, right? But this is exactly the same as this. So I'm going to rewrite that. Now dig this. This equals this. I can bring the I around front. And then I can rewrite this way. We've observed that before, that we can rewrite this E with cosine and sine. Okay? Now, also, x to the negative I can write this way, which I can then in turn write this way. Notice the only thing that's changed is the plus and the minus. And we have observed before that then we can put those together and get this. Now notice, here's x squared, okay, and x to the I, x squared, x to the negative I, and here's what our solution looks like. Okay, and I've derived this before for you, how that we go from this to this. I did it when we were working with homogeneous differential equations with constant coefficients. Okay. But there we have it. Okay. Now, more generally, if you come up with an m is alpha plus beta I, your solution is going to look like this. So notice in our example problem, our beta was 1. So it looked a little different. Okay. So in other words, we just had 1 log x right here. Okay, now let's look at a non-homogeneous case. So I go through here and I'm going to solve this like usual. I'm going to get my little quadratic equation, solve it, and I get m equals 1 or m equals 3. So here's y1 and y2. Now it's time to solve the homogeneous part. I need to find the particular solution. So I'm going to take my solutions here and say, okay, here's my particular solution for some u1 and some u2. Okay. Now, I'm going to use this variation of parameters, and here's what I need to do. I need to divide out the x squared. So notice here I'm dividing out the x squared, and I get the 2x squared e to the x to be my the f function. Okay. See, I just divided out the x squared, and I get this. Now, I'm going to use my formula now. It says u1 prime is equal to, now notice, 0. This is my column, u1, and this is the column u2. Or actually, let's do this. I've got a system of equations, and I'm going to put y1 over here and y2 over here. Okay. So now notice, I'm solving for u1 prime, And I've derived this in the past, so you can go back and see where these came from. But notice I put a 0 and 2x squared e to the x. I put that in the first column, okay? Because I've got y1 and it is associated with u1, okay? So in the first column. In the second column, I've got u2, which is x to the third, and then down here, the derivative of x to the third. Now in the denominator, I've just got y1, the derivative of y1. Over here, y2, the derivative of y2. See, that's the way we set it up. And that's the derivative. That's u1 prime. Now, I find the determinant. I multiply this minus multiplying this. And I get negative 2x to the fifth e to the x up top. Down on the bottom, I get 3x cubed minus x cubed. Putting that all together gives me this. Now, that's what the derivative of u1 is. I need to actually find u1, so what I want to do is integrate. So I integrate this one. And I pull the negative out front, and I'm going to use tabular integration here, integration by parts, and I get this. Okay? Here is u1. Now you see, this is a problem sometimes with variation of parameters because you have to integrate, and integration isn't always so easy. But now, so I say, okay, u1, y1, there it is. Okay, so that's part of our particular solution. Then it's time to look at u2 prime. So this time I've got y1, the derivative of y1, and over here in the y2 column, I put 0 and f of x here. Okay. Down in the bottom, same as for u1, and I just get e to the x. Ah, we like that integral. So u2 prime equals e to the x, therefore u2 equals e to the x. And now I notice I've got something wrong here. This is u2 y2. There we go. Yeah. So u2 is e to the x. Okay. Now, so here's what we've got. We've got c1x plus c2x cubed plus, now we do the particular solution. There is 2x squared e to the x minus 2x e to the x. And what I did was I just put these together. I put this together with this. And combine like terms, and this is what we get for our final solution. So there you go.